Okay, so welcome everyone at our weekly colloquium. Our speaker today is Professor Arul Lakshminarayan from Indian Institute of Technology Madras. So Professor is well known for his contributions in quantum chaos and quantum information theory, and today he will tell us about out-of-time ordered correlators, mutual information, and quantum entanglement. Please.
Thank you very much, Adam. Pleasure to be here again. It's an honor to come and visit such distinguished faculty. And so over the next hour, I'm going to talk about work which I did with a student here, Akshay Seshadri, who is now pursuing his PhD at the University of Colorado, and Vaibhav Madhok, who's a colleague of mine. And yes, so I will introduce some of these phrases which are now, you must have heard of them. It's a lot of activity around these concepts, and maybe they are saying something interesting. So we would like to explore that. And quantum entanglement has already been around for a long time, and we would like to see the connections of these to the entanglement. So roughly the outline of my talk is I give some motivation as to why to study these kind of questions and introduce the out-of-time order correlators and tripartite mutual information. Just very as briefly, and I should also say that I'm not an expert. Yeah. Out-of-time order correlators and tripartite mutual information. It's there in the next slide as well. Yeah. In fact, I believe people just refer to it as OTOCs, but I don't, because it reminds me of other things. I don't, for instance. So anyway, so I'm going to talk about all right. So right. And so I'm going to talk about these in the specific context of symmetric states and the quantum kick-top as a kind of a model for us to study it. One can study it in many different models, and people have been doing that extensively. So I'm going to talk in particular about this. And there was some conjecture about connecting the out-of-time order correlators with mutual information. So I'm going to discuss that in this particular context. Okay. So there's a lot of work over the last several years to understand thermalization in a closed quantum system. And this is, I would say, within that class of problems. And thermalization in an isolated system is driven basically by entanglement among the many constituents. So entanglement within many-body quantum states drives subsystems to thermalization, although the full state remains a pure state of zero entropy. So how does this happen? Essentially, some localized information, and I'm going to talk a bit loosely at this point, some localized information spreads within typical many-body systems fast. Well, I've put in here exponentially fast, but it need not be. It spreads within a typical many-body system, and in a sense, it scrambles. Okay, so it defines, if this sort of scrambling happens exponentially fast, it defines some form of quantum chaos. So I will come to specific ways of saying this, but let's, so maybe I will have more specific things to say. So out-of-time order correlators, which is related quite simply to commutator growth. I think that's a much more simpler way of looking at it. But it's a more general terminology, out-of-time order correlators, but it's related also to how commutators grow, as I will shortly say. Operator scrambling, which is how operators are getting more. Suppose you take an operator of a many-body system, but you take an operator of a single object in that. Obviously, because of some entanglement and interactions, it becomes a many-body operator. So how is this thing happening, and how fast is it happening, and so on is of interest. And tripartite mutual information, as I said, these are being vigorously investigated as measures of such delocalization of information. So, okay, in particular, I'm going to talk about some permutation symmetric states, and they are interesting to study because although they can be many body because of the symmetry, the rank of the subsystems is only linear in the dimensionality rather than exponential. So, for instance, suppose I have 10 spins, I have to deal with a Hilbert space of dimension 2 to the 10. But if they are permutation symmetric, I just have to deal with a 11-dimensional space. Of course, that reduces the problem size as well as it introduces some special features which we will see. And they occur naturally in spin systems with some collective variables. So let me start with some Hollywood here. So this is things about butterfly effect and chaos. And so this is related to the issues of scrambling. I believe there was a movie like this. I haven't seen it, but it says change one thing, change everything. And the butterfly effect, as you well know, has become a kind of icon of quantum chaos. Classical chaos, and supposedly popularized by Lorentz in 1960s, the meteorologist who first saw what we call the Lorentz attractor. But before that, I think in the 1950s, the science fiction author Ray Bradbury already had something which is today gaining some attention as a butterfly effect, and which is kind of related to out-of-time order correlators in the following sense, that the storyline is that somebody from the present goes hunting in the past using a time machine, of course, invented in, exactly, yeah. So invented in 2055, but he goes back to the Cretaceous period to hunt a Tyrannosaurus rex. Okay, so there's this huge beast coming at him, and he has this gun, which is, then he panics. He panics, and although there are rules, strict rules, because you're not supposed to change anything in the past. If you change something in the past, it can drastically affect the future. And therefore, he was not supposed to do anything. There's this very strict rules. However, because he panicked, he goes out of the path, and so there's some mess. And then when he returns to the present again, he realizes that things have changed completely. So there was a person who was supposed to take over as the president of the United States, who was a moderate candidate, and everyone was happy with that, and he was elected. But it so happened that when he came back, it was a completely opposite person who was running, who was elected. And then he realizes that there is mud on his shoes, and when he sees the mud, he sees a dead butterfly. So he has stepped on a butterfly there, and apparently it's okay to kill a dinosaur, but the dinosaur was going to die anyway, I believe, very quickly. But a butterfly, this butterfly changed everything and into the future. So this is, in a sense, time order, out-of-time order correlator does this. It makes use of going back and forth in time. But the Lorentz attractor is a more, it doesn't involve time travel. It's just a nonlinear system in 3 dimensions, and we know that there exists sensitive dependence on initial conditions. So any 2 initial conditions are very close by. After some time, it's completely far away. And this is, in fact, the meteorologist's excuse for not giving us the weather to, good accuracy. So that we know is sensitive dependence on initial conditions. Any small deviation in your initial condition in some phase space is amplified in time, but not only just amplified, it's exponentially amplified in time. And this rate of amplification is the Lyapunov exponent, and this is the trajectories separate in time. This is a hallmark of chaos. And it becomes all the more worse if the system is actually compact, and therefore these trajectories cannot just scatter away to infinity. They have to fold back, and then the whole phenomenology of chaos happens. For example, in these kind of systems, here are a very simple example of such systems. One doesn't have to look very far. You just have to look at a table of these shapes, and there is a free particle which is bouncing inside these, obviously called billiards. And a circular billiard, a rectangular billiard, or an elliptic billiard does not have such exponential separation of trajectories or chaos in it. The Lyapunov exponents are 0 in these cases. That's because of the additional symmetry in these problems. But if you break the symmetry by any means, for example, you break the symmetry of the circle by putting in a boundary there. This is the Sinai billiard, and then it's actually proven to be fully chaotic here with a positive Lyapunov exponent. Here is again a circle which is distorted into a stadium by these straight lines, fully chaotic. Again, a circle distorted into a cardioid, fully chaotic. So all of these are fully chaotic, and in fact, it is known that almost all systems with more than 1 degree of freedom are chaotic. They are ergodic, which means that phase space average is a time average, and they are mixing in the sense that, in the same sense as we take ink, let's say a drop of ink, put it in water, and it mixes. So you can think of ink as this A, and the mixing is this dynamics. Hamiltonian dynamics is what we will be concerned with. So this is the dynamics on that, and B is any subset in the water. So it mixes such that there is always that fraction of ink which is it's spread uniformly, so to speak, in that volume. So this is mixing, and it's different from ergodicity, and chaos implies mixing. And this rate of mixing is an important quantity and is given by these so-called Ruel-Polycott resonances, the rate at which such things decorrelate. Essentially, it's a decorrelation of these things. But there's also a nice observation, which I think is somewhat recent, at least in my knowledge, that chaos is also very evident when you look at Poisson brackets. So let's look at a very simple Poisson bracket.
So it's not a Hamiltonian system.
Which one?
If the Poisson bracket changes.
No, this is Poisson bracket with different time Poisson brackets.
X of t and p of 0.
Yeah. Even x of 0 will change. Anything will.
Doesn't change.
No, x of t, x of 0 also in general changes. Yeah. Yes. So. Yeah. So I mean, so this is essentially this. So if you take the Poisson bracket of x at a later time t with an initial, this is just this. But that is essentially your definition of how much x of t is changing when you're changing x of 0. That's your initial, that's your definition of Lyapunov exponents. So this would be exponentially growing if there is chaos. This is not, of course, true in general, but if the system is chaotic, this would be exponentially growing with a rate which is twice the Lyapunov exponent. Why this is nice is that this immediately tells us a way of going into quantum phenomenology, because once we go into the quantum, we don't have such phase spaces to deal with. We cannot visualize the position momentum thing. The very basic definitions of Lyapunov exponents are not well established then. I mean, or it's not clear because the whole stage in which this thing is happening, the phase space, is not there thanks to the non-commutativity of position momentum. So, of course, this is an old subject. It goes back to 1979 at least, the issues of quantum chaos. But there's been a renewal of this in the following sense of, let's come back to this issue of scrambling, or this many-body system in which there's some information which is localized. So here I give you a picture of some spins, let's say, and you have an initial state wherein you entangle only 2 of them. And then you let natural dynamics take over. It's still Hamiltonian unitary dynamics. But because of the interaction between these, it's going to, after some time, go into a very complex state wherein there is going to be all of these, this entanglement here is going to lead to a multipartite entanglement of the final state. So in this final state, if you were to ask, where is this information that there was a singlet here, it will be hard for us to find. Now, you may say, well, we can just go back in time because it's a unitary evolution. If we go back in time, we're going to recover the singlet. And in fact, that's absolutely true. However, if the system is in fact a very chaotic system or a non-integrable system, any small perturbations that may occur after some time may render such a thing of going back in time and looking at this system. I mean, you may not be able to recover this singlet. You could also ask questions like, how many spins do I need in order to reconstruct this thing, just from this state here? And this would be also increasing with time if the system is non-integrable or chaotic. So encoded information in the form of entanglement, or it could be encoded in some other way, like for instance, encoding just in the form of a state there, is now scrambled. So I just show some pictures from some old work of mine of such a thing where there's a Heisenberg chain, and we start with, in this case, 20 spins. So this can be done analytically. You start with a state where the first 2 spins are maximally entangled, others are not entangled. So here I'm plotting the entanglement between neighboring pairs of spins.
These are spin 1/2.
Yeah, these are just spin 1/2 qubit particles. Nearest neighbor, standard Heisenberg interaction. And you look at the nearest neighbor entanglement. Let's assume that there's a measure, and we know how to do that. And we do this. This axis is time. So initially, these 2 are entangled. The others are not entangled. And with time, you can see that there is actually a very nice transport of this entanglement across the spin chain. It's a closed spin chain. There's some kind of a reflection, and then it spreads around. So this information, so to speak, is kind of getting. Yeah, it's just a one-dimensional. No, it's an open boundary, so it comes back.
What is the boundary condition for spin? What precisely is meant by the open boundary condition for spin system?
Well, it just means that
To the last spin.
it is only interacting with the left one. It's only a question of interactions. So now, this system is not in any sense chaotic, or it's in fact an integrable thing. So let's look at what happens in a similar situation when there is actually non-integrability and chaos. This is again some old work with a colleague of mine from IIT Kanpur, V. Subramaniam, where we studied also Ising chains, but now the Ising chains were of 2 types, one in which it's integrable, another it's chaotic, okay, or non-integrable. In fact, the Ising chain, which is a transverse Ising model in which there's interaction, let's say, in the z direction, and there's interaction, let's say, in the x direction, is integrable. But if you put a field in a longitudinal direction as well, it becomes non-integrable. So that's what we are doing here. So what we are again starting with the same state of 2 spins which are initially entangled, and this is now time, and this is the entanglement between neighboring spins. Here there is a very different kind of a phenomenon because of the differences in these kind of systems. Here this is an integrable case. We are entangling these 2 spins, and then you can see that it spreads all over the place, but actually is never in a sense lost. It appears in some other time. So this is still very complicated, but we can actually have analytical control of this entire scenario. But when you start tilting the field and you have non-integrability and chaos, what you see is essentially that it is lost. That is, this is an entanglement between these 2 spins, remains for some time, spreads around, but after some time it's just completely lost. It doesn't mean that the entanglement is lost. It means that this bipartite entanglement has become multipartite. It's just gone into this kind of a state wherein it's suppose you take any 2 of these spins, the others are acting like a bath, and there is no entanglement between these 2. Okay, so that's what's happening. It's becoming like a thermal state in that sense. It's the other rest of the spins are acting as a bath. So I just wanted to give some concrete examples of what I'm talking about. So 2 of the measures which are currently used to study these kind of things, I would say not just these kind of things, but a wide variety of systems are coming back to this title, out-of-time autocorrelators and tripartite mutual information. So what are they? So this kind of a scrambling, how do we characterize it? So as I say, these 2 are, well, some 2 particular measures that people have studied. So one is growth of commutators of initially localized operators. Again, you could think of, in this case, you have a spin chain, and then you could think of an operator which is only sigma z on the first spin, and then evolve it with time, and then ask what is its commutator with sigma z at that point. But because it's now spreading all over the place and it's becoming a multipartite state, it is also changing. So that's essentially what we are asking. As you can see, this is like the Poisson bracket, the equivalent of the Poisson bracket being the commutator. So it's natural to study commutator growth. So the Poisson bracket squared was what was studied. So the commutator square essentially is what is being studied here. So I've put a trace here, whereas usually people put any state here, especially a thermal state, and do the calculations, because in a field theory they need not converge. But I'm just putting a trace here because, at least for whatever I'm doing in finite systems, and there is no issues with convergence. But otherwise, one can put some other state or a thermal state when doing this average. So it's very easy to see that this can be written as a difference of two terms. One which is a correlator, which is like this, a trace of the square of an operator at time 0, square of the operator at time t. So this would be a time-ordered operator in the sense that the operators which are coming here, this is larger time than this. Whereas the other term here is an irreducible term of this kind. It cannot be put into this form, where these 4 operators are being evaluated at times which are not in a monotonic sequence. There's time t, then 0, then again time t, and 0. So if you write this out in terms of, and this a of t is nothing but just the Heisenberg evolution of this a0. So if you write this out, you can interpret this as going backward and forward in time in order to calculate such a correlator. Although this correlator looks rather simple, but because of the fact that you will have to, in some sense, reverse time, it's actually difficult to measure this experimentally, although now there are many proposals to measure this, and also experiments which actually claim to have measured the out-of-time order correlator using some very nice methods. But this is the essential thing, that a commutator, for instance, can be written as a difference of 2 correlators, one which is time-ordered, another which is out-of-time order. And the key insight of people starting from actually Ovchinnikov and Larkin, I believe, in the 70s, and more recently to the high energy physicists as well as string theories, was that this behaved essentially very differently from this, in the sense that the decay of this can occur over a much longer time scale than the decay of this. In fact, if you think classically and just say that, okay, this is now a correlator at time 0, at time t, this decay should be essentially what I put in here as a mixing. So it should be really governed by the Ruel-Polycott resonances. And whereas the other one is something which is what is being extensively studied as the time. It's the simplest, in some sense, out-of-time order correlator. So, but this whole quantity itself is increasing for some time exponentially. So if this quantity is increasing exponentially for some time, this lambda is called a Lyapunov exponent. And if it is increasing exponentially till a time ts, that's a scrambling time, and beyond which the information is not locally retrievable. So basically, if you put some if you take some spin in some particular state, and after the scrambling time, if you just have access to that spin and maybe a few other spins still, it's not sufficient for you to reconstruct that state which is there. It's kind of the omelette has been made. You cannot reconstruct the egg from that. So there is this. It's related to the physics of black holes. And also surprising connections to black holes and the spin models, such as the Sachdev-Kiteve model, which is an all-to-all connected spin chain. And it's been calculated in field theories. And so it's an interesting thing that models of quantum chaos, which traditional models of quantum chaos have now expanded into these things, and people have calculated in many of these cases these Lyapunov exponents.
How does this depend on the number of spins? If you have very few spins, then probably you don't see this.
The Lyapunov exponent?
Yeah, you see, if you take 3 spins, for example.
Yes. You won't see. So it's actually a delicate question as to when you would see this lambda, and like for it's not also in fact it's essential to take, as people realized when you're doing spin chains and this, it's essential.
Spins, everything depends on your boundary conditions.
No, the same.
No, for 3 spins, it will not move at all.
No, actually it is.
Fix the middle spin forever. So there is no dynamics.
No, so it is no, for 3 spins it's too small a system to go into anything like it's just that it's quasi-periodic in a very strong sense. So you will not see any such an exponential thing. So so even for spin chains which are long, like 10 or 20, which is actually quite reasonable, if you take just one spin and its commutator at different times, you would see it's difficult to find lambda. However, if you take a larger number of spins, in fact, blocks of spins, maybe 1/2 of spins with the other, then it's easier to see this. So in a sense, to see the Lyapunov exponent in any of these models is also an art. So I think that the operators which have good quasi-classical limits are good operators to study these.
TSD depends on the size of the system.
Yes, so TS in particular depends on the size of the system.
Too small system.
So TS is in fact, this is the important time scale. So if the scrambling happens really fast, so this goes as the logarithm of the dimension of the Hilbert space. So this is what in quantum chaos is known as the log time. So it's known for a while, but in such systems which have no classical limit, so that is what is, I think, interesting, that there is no classical limit in these systems for us to visualize chaos, but it still has all the phenomenology which is associated with that. We can also calculate quantities like a Lyapunov exponent for spin chains, which would be otherwise hard to do. Okay, so just the other quantity which I talked about is mutual information, and it is so. This is a slightly different track now. It's about another way of looking at scrambling. Okay, so it's not more dynamics, but it has to do with just given the state, whether it is scrambled or not. So this is the definition of, first of all, mutual information. So we have, let us imagine, 2 random variables, x and y. And so the mutual information is the decrease in the uncertainty of x. So in the Venn diagram, this is x, and that's its uncertainty. That's y, and that's its uncertainty. But they could be correlations, and x and y can occur. So there would be, it's the decrease in the uncertainty given the knowledge of y. So it's essentially, it's equal to this area in this Venn diagram. Okay, so that's the mutual information. So this is the uncertainty in the variable x. This is the uncertainty in x given y, and so that's its decrease. And this is a standard thing. It can be written as uncertainty in x and y, and then you subtract this entire area of this thing, and you get this. So this is mutual information, and it's known to be always positive. And it's also symmetric. It doesn't matter with x and y. Tripartite mutual information is defined in the following way. Now we have 3 random variables, and we ask for the mutual information, let's say, of x with z. So what is the common information of x and z? Common information of x and y. And then we subtract from it the common information of x with y and z taken together. So this is, you see, very similar in structure to the mutual information in terms of these uncertainties. You take them, instead of these uncertainties, you take the mutual information itself. So this tells you a correlation between x, y, and z And although I have written it like this, it looks like X is preferred. It turns out that this is also symmetric under permutation of X, Y, and Z. That's easy to see if you go back and write what are these mutual information in terms of the uncertainties or entropies of these variables, and you see a very nice symmetric XYZ symmetric form. So this is known as the tripartite mutual information, has been studied in information literature under various names for a long time actually. But the interesting thing is it can be positive, negative, or zero, unlike the mutual information. What it is measuring, what is the significance of this is that if it is negative, then the information of X is spread more into Y and Z. That is, you have to take both the systems Y and Z together to get information about X. If you just have information of X from Z or from Y, that's not sufficient. So the information is kind of spread out. So this is the synergy, or the case when the whole is greater than the sum of the parts. So this is known as monogamous. It's like the entanglement is just as entanglement is shared, here also this mutual information can be shared. So if it is positive, however, then the interpretation is that there is redundant information. For instance, if two of these random variables are identical, then there is redundant information in this. So this is the interpretation. I have some further standard examples. For example, here, if there are three random variables, let's take three classical bits, which means 0 or 1, okay, with equal probability 0 or 1. If they are all equal, but they are still, each of them is random, then it's easy to calculate this tripartite mutual information. It's log of 2. This is in a sense like what I will be talking about as permutation symmetric states. In a way, there is, these subsystems are actually in some sense symmetric. And so this is having positive tripartite mutual information. Whereas if they are all independent and random, then there is no correlation. In the Venn diagram, there's no overlap. And this mutual information is 0. But here is an interesting case. If you take two of these numbers, random numbers, y and z, and you take I guess an XOR operation, y plus z modulo 1, and you keep this as the variable x, then x clearly depends on y and z. If you just give me the value of y, I won't know the value of x. If you just give me the value of z, I won't know the value of x. But I need both to know the value of x. And similarly, any pair. If I know x and y, I can know z, and so on. So actually here, the information of x is spread in y and z in a way. And turns out that in this case, the mutual information is negative. So this is a very simple example, and you can look at quantum examples of similar things, and you can see that if you have states in which entanglement is spread, for example, if you have four parties, A, B, C, and D, 4 particles, and they are all such that every mutual cut is maximally entangled, then it's easy to see again that this is having a negative tripartite mutual information. Whereas if there is no entanglement in some cases, you can see that it's 0, and in many of the cases which I'm going to present, actually they are positive. So the TMI sign was proposed by people also as, in a way, measuring scrambling, because now information is being spread out into various parties. And therefore, if there is scrambling, then this kind of a situation is occurring, and tripartite mutual information becomes negative. So there is actually no definite sign, I would say, for many body states or for field theories, but it has been found to be negative for conformal field theories with classical holographic duals. I'm not an expert on this at all, in fact, but you can look at these papers if you are interested. But also typical states of many body systems have negative TMI. Okay, that is actually telling us that negative, it's reflective of the fact that a generic state is in fact highly entangled. Okay, so due to the negative sign of the TMI or perfect states, this has been proposed as an alternative indicator of scrambling. So you can see this paper of chaos in quantum channels, which proposed such a thing. So we're going to check some of these things I have about 10-15 minutes, I think. I'm going to look at some of these quantities which I have introduced in a concrete model, where we also know a classical limit exists, yet it is in some sense a many-body system. So this is the model of the kick top, which has been studied by various people, including Marek Kush, who's here, but he avoids me every time I come here. So yes, mutually exclusive. And it's there in Hake's book. Carol has also studied a lot this system as a model. Is too large. It's just one large spin. You could think about it as it's just one large spin, but this is just a rotation about the y-axis. Whereas here it's a rotation. It's not a rotation, but it's a torsion, because it's a rotation about the z-axis, but the rotation angle itself depends on the angular momentum jz. And so, and also it's a time-dependent model that's essential to make it chaotic. So it's just periodically kicked. So it's a nice system which it's a Floquet operator. It's a time-periodic system, and but the interesting thing is, okay, you can also look at it as a collection of spin half particles, and therefore you can write a many-body Hamiltonian or unitary operator, which is this Floquet operator connecting states between the times of the kick, tau. Okay, so here is the unitary operator. That's this is the interaction from. So you can see that this is an all-to-all interaction between these spin half particles. There are two j of them, where j is the spin here, and this is coming from this rotation. So this is coming from this rotation. So this is in fact exactly like a transverse Ising model, except that the interaction is not just nearest neighbor, but it's all-to-all. So it makes it non-integrable in a very non-trivial way. And there is one parameter, which is this torsion strength. As the torsion strength is increased, it becomes chaotic. I believe maybe this mapping was first studied by Milburn and Wang, Ghosh, and Sanders in 2004, when they exploited this to look at chaos in a many-body system, look at entanglement and so on. I should also say that experiments have been done based on such a mapping. So here is the classical limit, which is the j going to infinity limit. It's just a map of the sphere onto itself, just the S2 onto itself. And this is the parameter kappa, which is here, kappa or k. And as this parameter is changed, so what is mapped, what is shown here is orbits on the sphere S2. So this is the sphere coordinates, theta and phi. And what is mapped here are many of these orbits. For kappa is small. Here it is, I believe it's 0.1 or something. So it's a very small kappa. So it's nearly integrable. And here it is 3. So it's quite large. So there is chaos everywhere. There are some regular regions. This is kappa is 6. It's essentially chaotic, mixing, and so on and so forth. Okay. So now the quantization is straightforward because they are just spin operators here. But now you see also this system has symmetry of permutation, because this is all-to-all interaction, and this one is there. So it's a permutation symmetric system, completely permutation symmetric system. And what we are doing is we are taking some initial state, which is in fact a coherent state, so that we have control over whether we are launching it from some chaotic region such as this or some regular region such as this. Evolving it in time, which just means taking powers of this unitary operator, because this is the propagator over one time step. So if you want to propagate over 100 time step, I just have to take u to the power of 100. So, and then I get the state psi, which is now a many-body state. And now from this many-body state, I can do all of those calculations of OTOC or tripartite mutual information and so on, and see how they behave with time. So that's the idea. So now in this case, we have taken 20 qubits in this thing. So it's a very simple system. Actually, 20 qubits is not large at all for this calculation because of permutation symmetry. And we look at subsystems of just 1 qubit. So that's the advantage of this mapping. So 1 qubit subsystems. Okay, we look at the mutual information, tripartite mutual information, so the tripartite mutual information is actually here. This is a case when the initial state is starting off from a regular region. So there's no chaos in this. And what you can see is that it behaves in some manner. And in fact, there is a hierarchy. The tripartite mutual information is here. These are mutual informations of A with B and A with BC. And this is the entropy or entanglement of subsystem A with the other spins. After all, entanglement is also a measure of what's happening to the scrambling. Okay, so one sees these oscillations, one sees that all of them are essentially giving us the same information, whether it's tripartite mutual information or it's entropy. And this is for regular. If you place it in a chaotic part of the phase space and do the same thing, this is now time, you see that again the hierarchy is maintained with the tripartite mutual information being here, other informations, and this is the entropy. The only difference is that there is a short time in which there is an increase and then a saturation. And what is more interesting to see is that the tripartite mutual information is also positive, whether there is chaos or no chaos. It's positive, it's 0.24 approximately. So unlike the cases where there was this thing about scrambling leading to a negative tripartite mutual information, here we find that actually the tripartite mutual information is positive whether there is chaos or not. Let's look at the out-of-time autocorrelator. Here the operators are the Jx collective operators. So collective spin operator Jx at time n and x at time n. So we look first at this picture here. There are 3 quantities plotted. One is this 2-point correlator, which is the time-ordered correlator. This one here. Okay, so that's what we call the 2-point correlator because it just involves 2 objects, and that has this behavior where it's a very short time. You can see that it's a short time, and then it's just oscillating afterwards, in essentially about this. Okay, whereas this is the 4-point out-of-time autocorrelator. Out-of-time autocorrelator has a much longer life in this, and by the way, this is for a spin system, large collection of spins. So this is 100 for each subsystem. There are 700 spins in this. So the overall system is 700 spins, and we take 100 spins and do this calculation. And this is the total out-of-time autocorrelator, or the commutator growth itself. So the commutator itself grows with time, and then it saturates. Now this growth is what is, well, it's also interesting to see what happens here, but the growth, if you look at it carefully, is exponential. So this is the log of this versus time. So you can see this exponential growth here reflecting the chaos in the system, or the Lyapunov exponent. So these are for higher values of the number of spins, 1,500 to 4,000. And you can see that this is and it matches well with the classical Lyapunov exponent. And this time till which it's going on, the scrambling time, is in fact just the log of the dimensionality of the space divided by lambda, which is Ehrenfest time in this case. So the information, it's interesting to see whether the tripartite information has information as to whether its growth, if it's exponential. Maybe the sign is not important, but the fact that it is also growing exponentially is important. So in fact, I think that is the case. We think that's the case, but we have not been able to find a clear exponent in that case. But we still think that it's actually, although here I said it's not exponential in this clean sense, but it's still happening at the same time scale as the growth of the OTOC. So I think I'll skip this part where we reason out why for permutation symmetric states the tripartite mutual information has to be positive. So in a way, we looked at subsystems of permutation symmetric states. We looked at their reduced density matrices, and the most important statement about this is that if you take, let's say, q qubits or q spins out of a large collection of n spins, the rank of these states is only q plus 1 at most because of permutation symmetry. And so it essentially behaves like what people might call an area law. So because it doesn't go linearly in the number of qubits of the subsystem, but as the log of the number of spins in the subsystem. So it's essentially like an area law, and this is a small entanglement compared to typical states. And this is what is actually responsible for this. So in fact, we have some estimates of how much that entropy is. And if you put that into this into the formula for mutual information, you get an estimate of the mutual information in permutation symmetric states of 3 subsystems, each of, let's say, size q, and it's quite an easy, it's a very easy calculation, in fact, to show that it's positive. And therefore, our reasoning is that marginal area law kind of entanglement prohibits negative TMI in typical symmetric states. So although there is chaos, definitely, out-of-time autocorrelators increase exponentially, yet the tripartite mutual information is positive because of the low entanglement within these things. So actually, maybe one can conjecture that permutation symmetric states are good states to maybe keep subsystem information alive, despite scrambling dynamics or chaotic dynamics in it. So just to conclude then, symmetric pure states have marginal entanglement, and they result in typically positive tripartite mutual information. They typically violate monogamy of mutual information. So as we have seen, TMI can be positive even when there is exponentially growing out-of-time autocorrelators and scrambling, as seen actually from a bona fide case of a chaotic system. I think I pressed... All right. So, well, all right. Just one, not even one. So further understanding will be useful for multipartite correlations. It's interesting to see what happens when one goes outside of permutation symmetric subspace. My feeling is that TMI will become negative in a very short while. So I hope I've given some idea that there are these are interesting quantities to study in many body systems. And thank you for your attention.
Okay, so do we have any questions or comments?
Did you look at any fermionic type of systems with anti-symmetry?
No.
So in the name TMI stands number 3 because it's 3-parted mutual information. Does it make any sense to consider 4 or 5
yes,
mutual order mutual information?
It, yeah,
and it works somehow in a natural way, or it's too complicated? Too complicated.
But yes, extensions exist. I think
because
within information.
we have kind of many body system, and then you distinguish number 3 in your measure. So therefore, you could ask whether 4 or 5
yeah,
body
so that's an
interaction
interesting
may
point
play.
because
Yes.
actually, if you look at tripartite mutual information and all the 3 parts make up a pure state, then it is 0. The tripartite mutual information is 0. So it's yeah. So it's so you need to always have 4 parts if you have a pure state to study tripartite mutual.
Okay, any other questions? If no, let's thank Arul once again.
Thank you.